All right, let's talk about the invisible force that runs the entire universe. It's the thing that builds stars, that sculpts galaxies, and, keeps you from floating out of your chair right now. We're diving into the absolutely incredible story of gravity. It sounds like such a simple question, right? But finding the answer has taken humanity on this wild ride, a journey that spanned more than 2,000 years and involves some of the absolute titans of science. It's the story of how we went from just watching things fall to understanding the very fabric of reality itself. So where are we headed? We'll start with the ancient Greeks, then jump to the revolution kicked off by Newton. After that, we'll get into the truly mind-bending world of Einstein's warped spacetime, see its wild cosmic effects, and finally land on the puzzles that are still keeping physicists up at night. Let's get into it. Okay, it all begins with the most obvious thing in the world. You drop something, it falls down every time. For centuries, the big question wasn't just that things fall, but why they do it. What's actually going on here? For almost 2,000 years, everyone just went with Aristotle's idea. He thought that objects had a natural place they wanted to get back to. So a rock falls to the earth. And, of course, heavier things fall faster. I mean, it makes sense, right? You see a rock and a feather, and it seems totally obvious. But then came Galileo, who wasn't just content to think, he wanted to test it. And he realized, wait a minute, the only reason a feather falls slower than a cannonball is because of air resistance. If you could get rid of the air, they would fall at the exact same rate. Now, Galileo couldn't just build a giant vacuum chamber, so he came up with this brilliant workaround. He rolled balls down ramps, inclined planes. This slowed everything down just enough for him to actually measure it carefully. And his results? Absolutely revolutionary. He proved that the acceleration due to gravity is the same for everything. And just like that, science became something you prove with experiments, not just with arguments. Galileo really set the stage for the next giant leap in our story, and this one comes from the one and only Isaac Newton. Because while Galileo explained how things fall here on Earth, Newton was about to explain why the moon and planets stay up there in the sky. This, right here, is the core of Newton's genius. The story of the apple might be just a story, but the insight is real. He realized that the force pulling that apple to the ground is the exact same force that's keeping the moon locked in orbit around the Earth. It wasn't one set of rules for down here and another for up there in the heavens. Nope, it was one single, universal force. And he boiled it all down into a beautiful, simple law with three key parts. 1. Universal attraction. Anything that has mass, you, me, this planet, the sun, pulls on everything else. 2. Mass matters. The more massive something is, the stronger its pull. And 3. Distance matters. A lot. The force gets weaker really fast as you move away. In fact, it drops off with the square of the distance. Double the distance and the force is only 1/4 as strong. And with this one elegant idea, suddenly we could predict it all. The orbits of planets, the paths of comets, and yeah, why an apple falls from a tree. But there was a catch. A big one. Newton's theory worked perfectly, but it had this kind of ghost in the machine. How did this gravitational pull work? How did the sun, millions of miles away, instantly tell the Earth to stay in orbit? It was like a spooky action at a distance. Newton himself was stumped, and this deep, nagging puzzle would stick around for more than 200 years. And that brings us to the early 1900s, and to a young patent clerk named Albert Einstein. He wasn't just going to tweak Newton's theory. Oh no, he was about to completely detonate our entire understanding of space, time, and gravity itself. So two major cracks were showing in Newton's beautiful theory. First, there was that whole action at a distance mystery. But second, there was a tiny, tiny problem with the planet Mercury. Its orbit wasn't quite perfect. The closest point of its orbit to the sun was shifting, just a little bit with every lap. We're talking an incredibly small amount, about 43 arcseconds per century, a fraction of a single degree. But it was there, and Newton's math couldn't explain it. And here's where Einstein's mind just changed the game. For Newton, gravity was a force. It was this invisible rope pulling things together across space. But for Einstein, there is no force. He said gravity is actually geometry. Mass and energy don't create a pull. They literally bend and warp the fabric of space and time itself. So space isn't just this static, empty stage where things happen. No, space is an active, flexible player in the game. The best way to picture it is the classic bowling ball on a trampoline analogy. You put a heavy bowling ball in the middle, and it creates this big dip, this curve in the fabric. Now, if you roll a little marble nearby, it's not being pulled by the bowling ball, is it? No, it's just following the curve that the bowling ball made. That's gravity. The Earth orbiting the Sun is just us following the straightest possible path through the curved spacetime created by the Sun. Mind-blowing, right? And the proof? It was absolutely perfect. When Einstein ran the numbers for Mercury's weird orbit using his new theory of curved spacetime, he didn't just get close, he nailed it. The math predicted an advance of about 43 arcseconds per century, exactly what we had observed. It was one of the most stunning confirmations of a new scientific theory ever. But general relativity was way more than just a fix for Mercury's orbit. It was a Pandora's box of predictions. Predictions so wild, so cosmic, that it would take the better part of a century for our technology to catch up and prove that he was right all along. First, in 1919, an expedition to watch a solar eclipse proved that the sun's massive gravity actually bends the path of light from distant stars as it passes by. Then, in 1971, we finally found our first black hole, Cygnus X1, a spot where spacetime is curved so intensely that nothing, not even light, can get out. And then, the grand finale. In 2015, we heard the universe. We detected gravitational waves, literal ripples in the fabric of spacetime, created by two black holes colliding. And just think about that number for a second. The ripples from that cosmic crash traveled for 1.3 billion years before they finally reached us and jiggled our detectors here on Earth. I mean, what an incredible confirmation of Einstein's vision. It's almost impossible to wrap your head around. So that's it, right? Case closed? Well, not quite. As amazing as general relativity is, we now know it can't be the final word. Because there are places in the universe, at the very extremes, where our best theory of gravity just breaks. And here is the fundamental problem facing physics today. We have two theories that are unbelievably successful. General relativity perfectly describes the universe of the big things: planets, stars, galaxies. It treats space-time as smooth and continuous. But quantum mechanics, which perfectly describes the universe of the tiny particles, says that everything, energy, forces, comes in chunky, indivisible packets called quanta. You see the problem? The universe can't be both perfectly smooth and fundamentally chunky at the same time. The two theories just don't play nice together. And we see the consequences of this clash when we look out at the cosmos. We see galaxies spinning so fast that, according to our understanding of gravity, they should have flown apart ages ago. So we have to invent an invisible dark matter to provide the extra gravitational glue. And then we see that the entire expansion of the universe is actually speeding up, being pushed apart by some mysterious dark energy. Together, this dark stuff seems to make up 95% of the universe, and we have absolutely no idea what it is. It's like the universe is screaming at us that we're missing a piece of the puzzle. And that leaves us right here, on the edge of the next great revolution. Will we ever find a single, unified theory, a theory of quantum gravity, that can finally describe everything, from a falling apple to a spinning galaxy to the inside of a black hole? The epic quest that started with Aristotle and was carried by Galileo, Newton, and Einstein is still going on, and the next chapter is just waiting to be written.